Hello.
Hello, Professor Burnett.
How are you?
Good, how are you, sir?
Doing well.
Okay, I think that works. And when is the first available time for him or her?
Oh, welcome everyone.
Hey, how are you?
Hello.
Special event, the presentation of the dissertation that Kang Liu will carry out in the next 2 hours, along with all other nice things, any questions and answers. So I see we have 3 committees here, and they don't have just one, right?
Professor, I think all the committee members are here.
So I see Professor Kapuczynski, Professor Yin.
Yeah, Professor Pradell is also here.
Yes, I'm here.
Okay, good to see you. So all of us are here. So
Yes.
unfortunately, it's the online meeting, but we'll try to run it as in person as much as possible. Namely, we will have now a breakout room that Kang will create for the committee members to discuss the situation and the dissertation and the candidate. After that, we'll go back to the general meeting, and at the meeting, committee members, and we'll go to a breakout room, and we'll result some examination. Is everyone okay with that? Okay. So can you create the...
Yeah, I will create this room.
You look very good on the screen.
Yes. So I guess you can see the invitation.
Mhm. So I hope all committee members to see that, and we click join, and we
Hi, all the audiences. Thank you for your attendance. We are just waiting for our committee members to have a little bit discussion before this presentation. So I guess maybe wait a little, like a couple minutes. Thank you.
大麦克小套。 Recording in progress.
Can you hear me now?
Yes, Professor.
Okay. All committee members are now here online.
I think Professor Yin is still not back.
I'm here.
Oh, yeah.
Yeah, they're here.
Okay, so welcome again, everyone. The committee member has met and discussed the details that we have to articulate before the meeting, and now we're ready to start with Kang's presentation. So please go ahead, Kang.
Yep.
Kang said that he would not mind questions being asked during the presentation itself. So if you wish, you can ask questions, both the committee members, of course, but also the audience. Questions for understanding you can ask during the presentation. Go ahead, please.
Thank you, sir. So this dissertation, hello everyone, good afternoon. This dissertation is titled The Alpha-Beta Precision Theory for Production System Monitoring and Improvement. This presentation is organized as follows. First, I will give the introduction, and then the main content is split into 5 parts. The first part is the alpha-beta precise estimate of 2 machine parameters, MTBF and MTTR. We include its definition, calculation, and observation time. The second part is called the alpha x beta x precise estimate of 4 system performance metrics, including machine efficiency, throughput, lead time, and working process. The third part is the estimate of machine quality parameter Q and quality parts throughput TPQ. Part 4 is the comparison of our alpha-beta precision theory with the Markov inequality, Chebyshev inequality, and simulation. The last part is concerning a specific type of production system that is practically important but theoretically neglected, which is production system with cycle overall. We included modeling, analysis, improbability, bottlenecks, and parameter estimation. And finally, I will give conclusion and future work. Introduction. In the field of production system engineering, machine parameters, including MTBF, MTTR, and also machine quality parameter Q, have to be estimated using machines' random up and down time realizations, and also parts quality measurements. And the estimate of those machine parameters can be used to evaluate the induced estimates of the system performance metrics, including machine efficiency, throughput, quality parts throughput, lead time, and working process. As we know that the machine parameters are non-stationary since the machine conditions are deteriorating over time. So we want to take the estimates in real time, and which means that we need to take those measurements as quick as possible, while obviously we want to maintain the estimate's accuracy. Unfortunately, the literature offers no methods for calculating the smallest number of measurements that can guarantee us to obtain reliable estimates of either machine parameters or system performance metrics estimates. So this dissertation is intended to provide such a method. The approach is based on defining the precision of an estimate by a pair of 2 numbers, alpha and beta, where alpha characterizes an estimate's accuracy and beta is probability. And using this notion, we can calculate the smallest number of measurements that ensure that we have the estimates of machine parameters or the induced performance metrics to be alpha-beta precise. Additionally, a specific type of production system, which is the ones with cycle overall, are studied in this dissertation as well. This cycle overall phenomenon would take place, for example, in the manual operations or automated operations with manual steps, which will make this machine cycle time previously a fixed constant to become indeed a random variable. So in this case, the alpha-beta precision theory for cycle overall estimate is needed. So in this dissertation, we also included modeling, analysis, improbability, bottlenecks of such systems, and also a case study that is motivated by an actual production system is also included. So part one, the alpha x beta x precise, the alpha beta precise estimate of MTBF and MTTR, definition, calculation, and observation time. Mean time between failures, or also called T-up, or mean time to repair, also called T-down, are used in almost every quantitative method for production system analysis. To evaluate the estimates of these two machine parameters, machine's random up and down time realization has to be measured in the average. So for example, the estimates of T-up based on n number of observations is the average value of the n number of machine's random uptime realization. So in this case, one question arises: what is the smallest number of measurements that is both necessary and sufficient to obtain these estimates with the desired precision? So to answer this question, we first have to define what is precision of an estimate. For example, the estimate of uptime based on n number of observations is alpha beta precise if it is bounded by alpha away from its true value. This inequality takes place with probability larger than or equal to beta. So for example, this expression here. And based on this definition of precision, the smallest integer n for which the above inequalities take place is called the critical number of measurements. We denote as n star sub t of alpha and beta, where this t represents t up or t down. So the first formal problem that we propose in this part is to evaluate this number for two cases. The first case is exponential reliability model, meaning that we assume the machine's up and down time are distributed exponentially. And also we want to investigate this number for non-exponential machines, specifically that has the up and down time coefficient of variation less than 1. It is also of our interest to evaluate the total observation time that we need to collect this n star sub t number of up and down time realizations. The approach we take is to first collect a small number of initial measurements, and then use this small amount of information to estimate the remaining observation time. So the estimate of the remaining observation time can be calculated as the total number of measurements that we still need to take, multiplied with the estimates of up and down time based on this small number of initial measurements. We characterize the relationship between the real remaining observation time versus its estimate using the following inequality here. This expression, that the real value is less than a safety factor A multiplied with the remaining observation time estimate. This inequality takes place with a probability larger than or equal to a desired quantity B. So we define the smallest initial number of measurements, which guarantees the above inequality is to be the critical number of initial measurements. So the second formal problem in this study is to evaluate this number for exponential machines. So for the first problem, the critical number of measurements for exponential machines is given by this theorem, which is the smallest integer that satisfies this inequality here. So as we can see that on the right-hand side of this inequality, there are no machine parameters, either machine uptime or downtime. Therefore, we have the corollary that this number is the same for both MTBF and MTBR of any value, meaning that once we take this n star sub t number of measurements on machine's random up or downtime realizations, then the estimates are always guaranteed to be alpha beta precise, no matter what the real machine parameters will be. Because this expression in theorem 1 is non-analytical, which is hard for further analysis, we developed a Gaussian approximation, which is given by this expression. We compare the true value versus this approximation for various pairs of alpha and beta, and we find out that these two sets of numbers are practically always the same for all pairs of alpha and beta investigated. Using this Gaussian approximation, we can draw the contour plot of this critical number for various changing alpha and beta. Some numerical example, if we want high precision, for example, alpha equals 0.05 and beta as large as 0.9, we need to collect about 1,000 number of measurements. If we lower the requirement, we select alpha equals 0.15 and beta 0.75, we only need to collect about 60 number of measurements. To extend this critical number for non-exponential case, we consider the following situation, that the machine's breakdown rate or the repair rate is an increasing function of time, which is the practical case. Then their resulting downtime or uptime will have the coefficient of variation less than 1. So the evaluation of these numbers are answered numerically. So we consider 3 possible distributions: Weibull, gamma, and log normal. And we use simulation to evaluate these numbers, which have been summarized in these 3 plots for these 3 considered distributions. And we have 3 observations that the first one is the coefficient of variation be the same, this critical number for the non-exponential case will always be the same practically, no matter what the distributions are. The second observation is, as the coefficient of variation decreases, this critical number also decreases. The third one is they're always upper bounded by this critical number for exponential ones, meaning that we use this number for exponential ones in practice, it will always work. So for the solution to this critical number of initial measurements, we have this following proposition, that if the total number of measurements that we need to collect satisfy this mild condition here in this expression, then this critical number of initial measurement is given by this expression. So we can also draw the contour plot for different total number of measurements that we want to collect. And we find out that for a large total number of measurements, it is possible to obtain a tighter bond on the remaining observation time. So for example, if I want a very tight bond, A, I only select 1.1 and probability B as large as 0.9. Then if I'm collecting a total of 200 number of measurements, this critical number of initial measurement wouldn't exist. But if I'm collecting a total on a level of 1,000 number of measurements, this critical number of initial measurement would exist. Part 2, the alpha x, beta x precise estimate of machine efficiency, throughput, lead time, and working process. So in this part, we consider a serial line with multiple machines where the precision of the induced estimates on machine efficiency, throughput, lead time, and working process are induced by the precision of the estimates of up and down time for each machine. If we assume they are alpha and beta alpha and beta precise for each of the machine, then we quantify these estimates of the induced system performance metric to be alpha x, beta x precise if this following inequality takes place. For example, if the estimate of E is alpha x away, is alpha E away from its true value, this takes place with probability larger than or equal to beta E. It is alpha E, beta E precise. So the first formal problem in this part is to evaluate this induced precision for all the 4 performance metrics. And the second one we call as the inverse problem, which is if we only care about the induced precision on the estimates of the performance metrics to be gamma and delta, what will be the smallest number of measurements I need to take on machines so that this gamma and delta precise of the only thing that I care about, which is the estimates of the performance metric to be gamma and delta precise. So if the solution to the inverse problem for the performance metric is less than this critical number for the same level of precision, then we call this performance metric to be variability contracting. Or if this inequality is reversed, we call this performance metric to be variability expanding. So let's look at the analysis for these 4 performance metrics one by one. The first is the estimate of machine efficiency, which is calculated as the estimate of uptime divided by the estimates of up and downtime. So we have this lemma that the induced alpha E is equal to 2 multiplied with alpha multiplied with 1 minus estimates of E. So we observe that if E hat is larger than 0.5, which is the practical case, then the accuracy on the E hat will always be better than the accuracy on the up and down time of the machine estimates. So for example, if E hat is equal to 0.75, then this induced alpha E, the accuracy on E hat is only half of alpha. If E hat is 0.9, then this induced accuracy on E is only a tenth of alpha. So for the induced beta E is given by this expression. As we can see, again, on the right-hand side, there does not exist any machine parameters, either T up, T down, or machine efficiency E. Thus, we conclude that this beta E induced is independent of machine parameters. For further analysis benefits, we also developed its Gaussian approximation of this beta E induced. We can also compare this set of two numbers for various alpha and beta on the machine's up and down time estimates. We observe, first of all, this beta E induced, this probability will be always better than beta for T up and T down for all the pairs of alpha beta we investigate. And also, this number is also practically independent of alpha. For example, this column that alpha varies from 0.02 to 0.1, this value is practically the same. And also, the approximation and its true value are practically the same for all pairs of alpha beta investigated. Solution to the inverse problem for E is given by this expression. We showed that if there E hat that is larger than 0.5, then this performance metric is variability contracted, meaning that for the same level of precision, we only need to collect a smaller number of machines up and down time. So we can show this property by comparing the contour plot of this critical number versus the solution to the inverse problem. So as we can see, for the same level of precision, on T up and T down, I need to collect about 1,000 number of measurements. But for E, I only need to collect about 20 to 200 number of measurements. As we can see that the expression for solution to the inverse problem contains this E hat estimates of machine efficiency. Without any measurements, we wouldn't know this value. Therefore, this expression is not a closed form. So some approximation have to be used in order to evaluate the solution to the inverse problem. So the approach is to first collect a small number of initial measurements and have a rough estimate on E. And then we add a safety factor to this rough estimate to make it a little bit smaller. And then we will have a little bit larger solution to the inverse problem. So we find from numerical illustrations that using this approach, this E hat precision will always be guaranteed, and this approximated value will be not that much far from its true value. So for system performance metrics, system throughput, we consider multiple machine lines with unreliable machines and finite buffers, as we know that the analytical evaluation of the performance metrics for such a system does not exist. So we use the recursive aggregation method, which is summarized in Li and Mirkov in 2009. The idea is to reduce the whole system into one aggregated machine. So this aggregated machine we regard is standalone throughput as the system throughput. The standalone throughput is computed as the machine's efficiency multiplied with its capacity. So one natural idea is to extend the analysis on E to this throughput estimate. So to bridge these two concepts, we introduced the notion of production system efficiency, which is the system throughput divided by the last machine's capacity. So in this case, the estimates are also computed as such. The estimate of ETP is equal to the estimate of throughput divided by the last machine's capacity. So if we take the alpha TP induced in the same format as alpha E induced, then we have this numerical fact that this beta TP induced will always be lower bounded by the beta E induced. And solutions to the inverse problem for throughput will be always upper bounded by the solution to the inverse problem for E. We have the following observation that if E hat for this system is larger than 0.5, which is the practical case, this performance metric is also variability contracting.
I have a question. Can you go back a slide?
Yeah.
So can you say something about this proposition? How does it come by?
So this proposition 2.7?
Yes.
So that is based on this numerical fact. So from our numerical analysis, we find this property that this beta E induced will be better. Thus, if we keep the same alpha, then the solution to the inverse problem will be better, meaning that we need less number of measurements compared with E.
Okay. All right.
Yeah.
Thank you.
Yeah. So, so here for the lead time and working process, these two performance metrics, we consider a simpler model, which consists of m identical exponential machines and infinite buffers. So in this case, we can derive analytical expressions for the lead time and working process. Some reminder, this lowercase lt is the relative lead time, and this rho is the relative raw material release rate. So using this analytical expression, we derive the alpha LT induced, which is given by this expression, and beta LT induced is given by this expression. Solution to the inverse problem is given by this proposition. And we also showed that if the system satisfies some mild conditions, then this performance metric is variability expanding, meaning that we actually need more measurements on the machine's up and down time. And then for working process, the alpha WIP induced is given by this expression, beta WIP induced is given by this expression, and solution to the inverse problem is given by this proposition. That we also showed that this performance metric working process is also variability expanding. We can list the solution to the inverse problem for each of these performance metrics and then compare that with this critical number. As some numerical illustration, we can also have some desired precision periods. And then, for example, for the same precision period, this column clearly shows this variability expanding or contracting property. So for this critical number, it could be on a level 200, but for the same level of precision on E and throughput, it only requires certain number of measurements. But for the lead time and working process, the critical number would be about 1,000. Part 3 is the alpha Q beta Q and alpha TPQ beta TPQ precise estimate of machine quality parameter Q and quality parts throughput TPQ. So we consider in this part a non-perfect quality machine that can produce quality parts with probability Q and defective parts with probability 1 minus Q. And then the estimate of this Q is calculated as the quality parts that we measure divided by the total number of parts that we measure. We qualify it to be alpha Q beta Q precise if a similar expression takes place. And this smallest number of n is denoted as the critical number of quality parts quality measurement. So the first problem in this part is to evaluate this number. And then we consider the quality parts throughput, which is the performance metric for a serial production line with multiple non-perfect quality machines, which only for each machine's Q, the alpha Q beta Q precise of this Q are available. So in this case, the estimates of quality parts throughput is equal to the throughput multiplied with each machine's estimates of the Q. So we quantify that to be alpha Q beta Q, alpha TPQ beta TPQ precise. And so the second problem is to evaluate this induced precision for this performance metric and solve the inverse problem, and also to characterize the variability property. So the critical number of quality parts.
What is the inverse problem? Can you describe a bit?
Yeah, so which one? I'm sorry.
The inverse problem for TPQ.
The inverse problem is what number of measurements that we need to collect for these quality parts for each of these machines, so that this performance metric is the given gamma and delta precise that we cared about.
And here exponential machine means the service is exponential?
It means the uptime and downtime distributions are exponential.
Okay.
This quality model is actually Bernoulli.
Okay.
Yeah, thank you. So this critical number of quality parts measurement is given by this expression. Some numerical illustration, if alpha Q is 0.1, beta Q is 0.9, then this critical number could be about 100. And then the induced precision for TPQ, the alpha TPQ induced is equal to K multiplied with alpha Q, where K is the total number of machines that are non-perfect. And this beta TPQ induced, we showed that it is lower bounded by this expression. Solution to the inverse problem is given by this expression. And we have the following observation that if we have more than one non-perfect quality machine in the system, then this performance metric is also variability expanding. So we show that property using some contour plots for solution to the inverse problem and also this critical number. For the same level of precision, this solution to the inverse problem could be about 500 number of measurements, and then this n star sub q could be only about 100 number of measurements. So we can also compare the formulas for this critical number versus the solution to the inverse problem, and also some numerical illustration for this variability expanding property. So thanks to Professor Ying's suggestion, this part 4 is added to this dissertation, which is the comparison of the critical number calculated using the alpha beta precision theory versus those evaluated using Markov inequality, Chebyshev inequality, and simulation. So in part 1, we evaluated this number using our theory. Since the estimates of up and down time are random variables, their statistical characterization can also be obtained using classical probabilistic inequalities. For example, Markov and Chebyshev inequalities, as well as, since this is a random variable problem, we can also use numerical simulations. So this leads to the possibility of evaluating this critical number using those three mentioned tools. So this part is to carry out this evaluation and compare the results with those that is derived in part 1. So as we mentioned, this estimate of T up and T down are alpha beta precise if these inequalities take place. And then using the theory, this critical number is given by this expression. We denote the critical numbers evaluated using Markov inequality, Chebyshev inequality, and simulation by n star sub Tm representing Markov, and then n star sub Tc, and then n star sub Ts respectively. The former two numbers are characterized analytically, and the third one numerically. So the first number, this n star sub Tm, is given by this expression. N star sub Tc is given by this expression. And this n star sub Ts can be obtained using a combination of Monte Carlo simulation and line search. So this will be the smallest lowercase integer n that satisfies the following: that the total number of times this estimate of odd time based on this lowercase n number of observations is bounded by alpha away from its true value, divided by the total number of times that this experiment is conducted. This number will be larger than or equal to beta. So we can put these three sets of numbers for various alpha and beta. First, this plot on the left is we fix beta to be 0.9 and varying different alpha. And also this second plot is to fix alpha equals 0.1 and vary beta. And then the critical number evaluated using our theory is marked in this red dash line. So as we can see that this n star sub T, M, and C are much larger compared to the values evaluated using simulation or our method. And we can better illustrate this property by showing some numerical examples. As we can see that these first two sets of numbers are much larger, and the simulation method and our method would have approximately the same result. Thus, we conclude that using those probabilistic inequalities, we can only obtain approximations of these critical numbers, which are much larger compared to those obtained using our theory. Using simulation, it would have these following disadvantages. First, the computation time complexity for simulation is capital N, lowercase n log lowercase n, where this lowercase n is where you start your line search algorithm. And then using our theory, obviously the computation time is constant. The following table shows the computation time for various of tasks using these two methods. As we can see that using the simulation is orders of magnitude longer time to evaluate these numbers. The second disadvantage is the result is subjected to the randomness in the simulation. And the last one is, since there are no analytical expression for this number is available, we cannot derive any property of this number as a function of alpha and beta, or for every different value of t up and t down, we have to start this simulation anew. So the last part, production system with cycle overall, modeling analysis in probability, bottlenecks, and parameter estimation. Variability of production system usually comes from two reasons. The first one is the unreliable equipment, meaning machines goes randomly up and down. And another reason is the random parts processing time, also referred to as the cycle time. So the former reason is the basis for system theoretic approach for production system performance analysis. And the second reason is the basis for queuing theoretic approach to the performance analysis. In practice, however, another source of variability can be observed, which is cycle overall. So in this case, the total part processing time becomes a summation of a fixed nominal machine cycle time plus a random duration. This situation will wildly occur in the practice, for example, in manual operations or automated operations with manual loading and unloading steps. There are two main features that characterize this phenomenon. The first one is at the beginning of each cycle, this phenomenon may or may not take place. And condition on that it take place, its duration will always often related to its the machine's nominal cycle time. Usually it is either a fraction or a small multiple of this machine's nominal cycle time. So this feature makes the queuing theoretic approach and system theoretic approach that have been developed inapplicable to this kind of system with unreliable machine and cycle overall. So in this study, we first proposed our mathematical model for such kind of unreliable machine with cycle overall. So the model is defined by three sets of assumptions or parameters. The first one is nominal parameters, including machine's nominal cycle time and nominal capacity. The second is reliability assumption. We assume the machine's up and down time distributions are distributed exponentially. And at last is the parameters and assumptions concerning cycle overall. So at the beginning of each cycle, we assume that the overrun would take place with probability POR. And then condition on that it take place, its duration we assume to distribute exponentially with its expected value equal to a small multiple KOR multiplied with machine's nominal cycle time. So in this case, this mathematical model can be summarized by a set of 5 independent parameters: tau, T up, T down, POR, and KOR. So in order to do performance analysis, we want to simplify this mathematical description. So we consider in this study 2 simplification methods. The first one, which is widely used in practice, is to embed this cycle overrun into machine's downtime. The second one we propose in our study is to embed this cycle overrun into machine cycle time. So these 2 expressions are the ones if we embed the cycle overrun into downtime for the calculation of machine efficiency and standard loss throughput. And these 2 are for embedding this overrun into cycle time. So the errors using the first simplification method in terms of standard loss throughput is evaluated using this expression. We picked some machine and cycle overrun parameters and find out that in terms of standard loss throughput, this error can be between 4 to 27%, which means that what have been practically always used, actually from a standard loss throughput standpoint, it introduces large error. We have the following theorem that says the exact standard loss throughput for the machine that is described by our mathematical model is computed using this expression. So we find out that it is exactly equal to the standard loss throughput if we embed the cycle overrun into machine cycle time. So from a standard loss throughput standpoint, we can simplify our model by a set of triple parameters that are tau plus POR times KOR times tau, and then machines T up and T down. We refer to this as the simplified parametric model of such machines. Whether this simplified parametric model works for serial lines performance analysis is answered numerically in this section. So the simplified parametric model performance metrics can be obtained using aggregation, and the one following the full model can be evaluated using simulation. So we selected these 4 performance metrics: throughput, working process, blockage, and starvation. The errors using the simplification method are evaluated using these 4 expressions. We consider here the number of machines in the system M equal to 2, 3, 5, 10, 15, and 20. And for each of these cases, we randomly generate 100 lines with machine and buffer parameters equal probably selected from the following sets. We observe that for each of these M, this error is between, for the throughput, this error is between 0.29 to 4.26. And for working process, this error is between 1.72 to 14.37. And for blockage and starvation, the errors are always less than 0.07. So we conclude that for serial lines with machines that are less or equal to 20, this simplification method actually works in practice for production system analysis. So then let's consider the improvements of such machine. So for standalone throughput improvement, we have this following theorem, which is referred to as the standalone throughput SAT improvability indicator, that says if T down divided by T up is less than POR multiplied with KOR of this machine, then for the same fraction of reduction for either the cycle overall or the downtime, the overall reduced machine would have a larger standalone throughput. And if this inequality is reversed, then it is preferable to reduce the downtime of the machine. So for the throughput of the serial lines improvement, we consider 2 steps. The first one is to identify the bottleneck of this system, and then to improve the bottleneck in order to improve the whole system throughput. So the bottleneck is defined as the machine that has the largest partial derivative, partial throughput, partial machine capacity, meaning that improving the machine capacity, the bottleneck machine will be the one that introduces the largest throughput improvement. There is a bottleneck identification procedure that is summarized in Liu and Milkoff 2009 for production systems with unreliable machines. So the first step is to evaluate the blockage and starvation of the system. And then we assign an error pointing from this machine to its downstream machine if this machine's blockage is larger than the downstream machine's starvation. If this inequality is reversed, then we assign an error from the downstream machine pointing to this machine. So after we assign errors for all the machines in the system, the one with no emulating error will be considered as the bottleneck. If there are multiple machines that has no emulating errors, the one with the largest severity, which is defined as the difference between this machine with its peripheral machine's blockage and starvation, the largest severity machine is considered to be the primary bottleneck. So whether this identification procedure works for our system is answered numerically in this section. So we consider M equal to 3, 5, 10, 15, and 20. For each of these cases, we randomly generate 20 lines using the above mentioned method. And for each of these 100 lines generated, we identify the bottleneck using this procedure and assess its accuracy by comparing the bottleneck machine with the one identified using the numerical evaluation of the partial derivatives. So as it turns out that in all these 100 lines, the procedure, the numerically identified bottleneck is at least one of the bottleneck identified by the procedure, because this procedure can possibly produce multiple machines that has bottlenecks, multiple bottleneck machines in the system. The following table shows the number of lines where the primary bottleneck identified by this procedure is actually the bottleneck of this system. So based on this result, we conclude that in practice, this identification procedure works for our system. And then we consider improve the bottleneck machine based on the standalone throughput improvability indicator. So whether this will hold in the framework of serial line is answered numerically. So for the above mentioned 100 lines, we reduce either the downtime or the cycle overrun by 10% of the bottleneck based on this improvability indicator. The following table shows the number of lines for each case where this indicator turned out to be optimal. So based on these results, we conclude that in practice, these two steps, the first identify bottleneck and then improve bottleneck machine based on our indicator actually works in practice. And then is the parameter estimation. The estimates of POR and KOR are alpha beta precise if the following two similar inequalities would take place. And then the smallest integer for which the above two inequalities take place is referred to as the critical number of cycle overrun measurements for POR and KOR respectively. These two numbers are given by this proposition. And consider the unconditional mean of the cycle overrun, which is calculated as the estimates of POR multiplied with estimates of KOR multiplied with tau. We quantify its precision by alpha OR and beta OR. And then this the induced value are given by these two propositions. Solution to the inverse problem is given by this proposition. And we conclude that this performance metric is also variability expanding. So finally, we put our proposed method into a case study that is motivated by an actual production system. So some preliminaries. Due to confidentiality reasons, all the machine and buffer parameters have been modified. However, we preserve the qualitative feature of the actual production system. Due to those modifications, the system throughput can be measured. The system throughput that we have already been measured from the factory floor cannot be used for the validation of the mathematical model that we propose for this production system. Therefore, we created what is referred to as the digital twin system that is populated by the modified data, and we regard this as the real system for this case study. This is the structural model of the modified production system. As we consider that in this system, there are 12 machines. So this is 1 out of 8 weeks raw data that is already modified as a numerical illustration. By observing those data, we find the following interesting facts, including that out of these 12 machines, there are 7 that experience cycle overrun. And the longest overruns are in machine 6 and 10. For model validation, the throughput of the digital twin system can be evaluated using simulation. And for our mathematical model, the throughput can be evaluated using aggregation. So we find out that the error are always less than 3% for all the 8 weeks. Therefore, we conclude that this model is validated. So since it's validated, we can have some performance analysis for each of these weeks. We find out these following facts. For example, for the last week, the primary bottleneck is the machine 6. Although it has high efficiency, its standalone throughput is small due to its large overrun. And for all the 8 weeks, this throughput is substantially below the smallest standalone throughput of all the machines in the system. Then is some data pre-processing. We observed that this data for each machine exhibits substantial variability. Therefore, some pre-processing is needed because we don't want to design projects that improve the throughput and 2 weeks later find that they are no longer valid. So this is accomplished by averaging 4 weeks data. So we can do some performance analysis on this average model, and we find out that first of all, the bottleneck is machine 1. The whole system throughput is about 15 joule per hour. Since we know that nominal throughput of this system, which is computed as assuming there are no machine breakdown or cycle overrun, is 30 joule per hour, the throughput losses are over 50%. And from our analysis, we find out this job losses due to downtime is about 8 joule per hour, and due to overrun is about 3 joule per hour. we set the goal in this project to design continuous improvement steps that lead to 5, 10, 20, and 30% throughput improvements. For the designing of the continuous improvement project, we use the following steps. First one is we identify the bottleneck, and then we decide to decrease either downtime or cycle overall using this indicator. And then we calculate this improved throughput of the aggregated of this proposed model. And then if this throughput improvement actually satisfies our goal, then we will stop. Otherwise, we will start from the first step. The following table lists the improvement steps that we need to take if we want to have 5, 10, or 30% throughput improvement. For example, if the reduced downtime, if we want 5% throughput improvement, we would have to do work only on machine 1, including reducing its downtime by 35% and reduce the cycle overall by 20%. And also, if we want 10% throughput improvement, we would have to do work for 3 machines, first, the second, and the sixth, including the steps of reducing the first machine downtime and cycle overall, the second machine's downtime, and the sixth machine's overall. So those projects are given to the production system managers for the suggestions, as a suggestion, and they can decide what kind of project that they want to introduce to their systems. So the conclusion and future work, the quantitative results that has been obtained have been discussed throughout this presentation. As some qualitative conclusions, the following 2 items can be mentioned. The first one is this dissertation provides techniques for production system monitoring for the purpose of system improvement. And in addition, this dissertation develops methods for performance analysis and improvement for a class of practically important but theoretically neglected type of a production system, those with unreliable machines and cycle overall, and illustrates by a case study the potential utility of the methods that we developed. For the future work, one possible direction is to extend the analysis and evaluation of these critical numbers to assembly system performance metrics and also to machines that are non-exponential, and extend the analysis and improvability bottleneck identification procedure to assembly system with cycle overall, and to those systems that has overrun that are distributed non-exponentially. And finally, we would like to apply this alpha beta precision theory to practice and merge them into the automotive production system monitoring and improvement softwares. So at the end of this presentation, I would like to thank my academic advisor, Professor Mirkov, for his years of support and also efforts, guidance, help, and even patience that he put into this work. And I also want to thank my committee members, Professor Kupaczynski, Professor Preden, and Professor Ying for their valuable suggestions and time. And also my co-authors, Professor Yoon from DJIST of Korea, Professor Liang Zhang from University of Connecticut, and Dr. Alavian, who has already graduated from our group. And also, I would like to thank the audience for your attention. So if you have any questions, you can ask.
Well, thank you, Kang. Very efficient and effective presentation. You did it less than in an hour, which is remarkable. Thank you.
Thank you, Professor.
Okay, questions, please, from the committee members. And after that, we'll have questions from the audience as well, if any.
I had a couple of questions in the future work slide.
Yeah, this is
can you say how do you plan to address the non-exponential systems?
So I think from our part 1 analysis, we find out that as long as the coefficient of variation is the same, actually it can be shown in theoretically that it will have this critical number that is less than the one for exponential. The exponential machines would have coefficient of variation equal to 1. So using this kind of inspiration, we can maybe show the variability of each of the performance metrics are further contracting or keep the expanding property. But I guess at least the upper bound, which is the one using exponential model, can be a guide, and also the relationship between the coefficient of variation and the critical number can be derived theoretically.
Okay. Yeah, thank you. I don't have any more questions.
Thank you, Professor Perget.
Anyone?
All right, maybe I can go next.
Please.
Yeah, okay, thanks. So, I have a question on the comparison. So you compared with Markov inequality and Chebyshev inequality. I was wondering, have you considered compare the result with the central limit theorem? There's a finite sample result called the Berry-Asim theorem, which tells you how fast the distribution converges to the Gaussian distribution with given number of samples. So maybe that's also something worth considering as well.
Yeah, thank you. Yeah, so I think that's a very good suggestion. And also this critical number that we evaluated in the first theorem, this is the exact number. So we already have this exact number. Yes, using this central limit theorem, we can have these approximations that as this total number of observations that we need to collect increases, this will be more and more close to our exact value.
Yeah. So another comment, maybe or question to follow what Sandeep asked. Maybe in the case which the distribution is not exponential, well, it's possible to look at like phase type distribution. So you have multiple phases, but each phase is an exponential distribution. Because we know
yeah. So I think in theoretically, so for example, using a central limit theorem, so as long as the coefficient of variation is the same, they should have the same, practically the same critical number. So also for the multiple phase, multimodal distributions, this I think should always be the case. Should also be the case.
But the will space-time distribution, if it's solvable, give you a better estimation than just use the exponential distribution.
Yeah, I think theoretically, for exponential ones, it is possible to derive these theoretical critical numbers. So for multi-exponential distribution that is combined, I think maybe it is also possible to derive this number. Yeah.
Okay, thanks. Yeah, that's all.
Yeah. Thank you, Professor.
Anyone? We have a full hour of questions now, which I don't suggest you to be here, but a full hour, but we have time. Okay, maybe the audience has some questions. Don't be shy. It's a friendly audience here, including the members of the committee. But don't be shy.
So I was able to figure out how to unmute my mic. Still following up a little bit on the previous thread. So when you compared coefficient of variability smaller than 1 with exponential, this kind of clear. CV smaller than 1 to some power is still smaller than 1. When you just think about your base cases and coefficient of variability is bigger than 1, probably you could do similar comparisons. The question is, what would be the power? Is there some kind of uniform way of thinking that basically it would enter linearly or quadratically in your estimates that you provide?
Yeah. So from the analysis, actually it can be shown this tendency, this rate for changing as coefficient is changing, how this critical number is changing. It is as the tendency of this inverse error function. So using, for example, this central limit theory, we can show that this is the this is the rate for this relationship.
Yeah, so I kind of understand that, but does it imply that if, let's say that you have something which is coefficient of variability equal 2, and then basically you cannot tell, of course it will be, the errors will not be smaller than the ones estimated for exponential, but they will be bigger, but they will be twice as big, 4 times as big, or there is no way of telling basically.
Yes, so the way is as the coefficient of variation grow linearly, this critical number will grow in the rate of inverse error function. So, for example, this coefficient of variation is 0, then this critical number is 0. As they go to infinity, this will grow. I think.
So the question is whether it will grow polynomially with a constant coefficient or not.
So this is the inverse. So I think the rate will be decreasing.
Well, that's clear. The question is with what coefficient? Yeah.
Yeah.
Yeah. Well, if you don't know that, that's fine. It's just like, you know.
It's very easy to check that. I think it will. So the only thing is I don't remember is that
well,
inverse or the actually not inverse error function.
Yeah,
so,
I was trying to kind of take advantage of you having it on top of your head, but that's not so crucial.
Yes.
Thank you, brother. Thank you.
But if I may, Roman, let me mention that, of course, as you know, in queuing theory, all the performance metrics are evaluated as a function of square of coefficient of variation. So
correct.
Now, but and of course we have some not in this work, but in some other work that we've done, we have saw it as well. Now, but we use practically always cases with CV is less than 1, for the reason that Kang mentioned, that if we assume that we have a random variable where the transitions between various states, the rate of transition is monotonically increasing in time, like machine is in working condition, and after that it goes to another state, broken down. So the if this is monotonically increasing rate of transition, in this case, I may not even know what is the distribution of this random variable lifetime or resident time will be, but I do know, and this is a theorem, that the coefficient of variation will be less than 1.
Correct, but for infrequent events, basically, coefficient of variability, basically, so infrequent events with constant breakdowns will easily have coefficient of variability bigger than 1. So basically,
no. When the constant transition rate, in this case, the coefficient of variation is equal to 1, because constant transition rate is exponential distribution.
Yeah. No. So the question is, we know basically how these behave, but the question is, when there's underlying basically variable, and then you want to evaluate different let's say efficiency or throughput, it's not quite clear whether this nonlinear transformation will change the coefficient for variability from linear to quadratic to sublinear. Just, I mean, basically it may depend on this specific transition.
Yeah, that's what queuing theory tells us. This is square coefficient of variation is involved. It depends upon the problem. We're talking about the problems related to the cases where the residence time, when it increases, the probability of transition, it also increases, which is natural. You know, the older your car is, the larger the chance that it will break down, right? Everything is like that. And there are some experimental results that people studied reliability of equipment on the factory floor. And practically always they experimentally determined that the coefficient of variation of up and down time was less than 1. And this is what created our interest in proving this thing, that this is indeed, it's not just by chance, but this is because of this property that transition rates are increasing with time in this class of system. Not always it's like that, of course. Like you can have Weibull distribution and selecting various parameters that give you distribution with CV whatever you want, 10, 20, or 0.1. This is, and in fact, well, this is maybe a different story. Some other QMP systems, people saw phenomena like that. But this is the reason why. And I agree with you, it will be interesting to see. And we did something that if you look at the throughput as a function of CV, in the range of CV between 0 and 1, it's practically linear, so not exactly. But when you will increase CV beyond 1, in this case, it becomes a nonlinear, like inverted parabola type behavior. So this is what the quadratic coefficient operation comes in the picture.
Okay, thank you.
Now, committee audience, maybe some more questions? No. Okay. So with your permission, ladies and gentlemen, maybe I'll thank all of you for attending this presentation. Of course, Kang, thank you very much for a masterful, from my point of view, presentation. Thank you. So now, Kang, would you please create again?
Yeah.
Well, we will not do that like that. Maybe we will go now to a different Zoom meeting with the committee members. We will discuss the results of this presentation, and after that we'll come back to this current meeting and we'll announce what are the results.
Okay, if that's what you prefer.
Yes, this is what we thought that we will do. So now
I'm going to start the meeting, Simeon.
say it again.
I'm going to start that meeting.
You're ready to start? That's what you're saying?
Yes, I'm ready to start.
Okay, and I want to answer the screen.
I will leave and I will have to leave this meeting and I will start the meeting. Okay.
We have to leave this meeting, right?
Yes. Yes.
Okay.
Yeah, I'll do it now. I'll leave and join.
Leaving the meeting now and go to yours. And after that, we'll come back, ladies and gentlemen.